Greetings, science family. We wanted to jump into gas laws worksheet. We've been talking about Charles' law, Boyle's law, and Gay-Lussac's law. I wanted to do one example of each and pick out one that sometimes gives people a little bit of trouble. So today for Charles' law, we're going to focus in on question number 3. So let's go ahead and get to it. So if we say and look here, number 3 says calculate the decrease in temperature when 2 liters of a gas at 20 degrees Celsius is compressed to 1 liter. So first of all, 2 liters of a gas is going to be my starting volume, and it's at 20 degrees Celsius is my starting temperature. We're then going to squeeze that volume smaller down to 1 liter, so that's my volume 2. So we want to know what the new temperature really is. So I guess that's going to be our question mark. As we know, V1 over T1 equals V2 over T2. That's going to be Charles' law. And the reason that we're not going to deal with pressure is because it has nothing to do with the problem. And we're also assuming that pressure is going to be constant. And that's something that we know is said at the very top of this worksheet for this section. Pressure is being held constant. All right, so let's start plugging in. For our V1, we have 2.0 liters. For our T1, we have 20 degrees Celsius. Now remember, 20 degrees Celsius isn't the proper unit. We need to convert that to Kelvin. So that means 20 plus 273, we really need that as 293, all right? So we'll keep that as a side note. Now over here, the new volume is 1.0 liters, right, for V2. And T2, we actually don't have. We're going to solve for that. So to solve for T2, we could cross multiply, right? So that's going to be 2.0 times T2 equals, and over here's the cross multiply, that's going to be 293 times 1.0. All right, so let's start simplifying this. 2.0 T2, we can't do anything there. 293 times 1 is just 293. Let's get T2 by itself, so let's divide both sides by 2.0. And when you end up getting that, the new temperature should be 293 divided by 2, which ends up being 146.5, and the units are in Kelvin. Now, calculate the decrease in temperature. Technically, I gave my answer as this for the new temperature, but I guess it's really asking what's the decrease. So if I started at 293, and I went down to 146.5, the change in temperature really is, the decrease is 146.5 because it got cut in half, right? So the change in temperature was actually 146.5 degrees Kelvin. But in the end, we're using Charles' law there, and we're using that cross multiplying to help us figure out and solve for the problem. Okay, but that was an example of Charles' law. Let's move on to Boyle's law. If we jump to number 10 on our worksheet, this is a Boyle's law problem. We want to know what pressure is required to compress. So compress means to smush down, but you've got 196 liters, so that's a volume. 196 liters of air at 1 atm, so that's a pressure. And you want to compress it into a cylinder whose volume is 26 liters, so that's a new volume. So I guess what we really want to know is what is going to be our second pressure? Well, if we know Boyle's law, since temperature is held constant, notice it's not really mentioned in this problem. P1 V1 equals P2 V2. We also know that the pressure goes up as we smush the volume down. So we should see that inverse relationship. So let's start plugging in and seeing if we can see that actual relationship. So for P1, it's 1 atmosphere. For V1, it's 196 liters. For P2, we don't know what that is, so we're going to leave that as our variable. And for the V2, new volume, it's going to be 26 liters. So notice we're going to go from 196 to 26 liters. 1 times 196 is 196. And if we want to get P2 by itself, we're going to divide both sides by 26. So P2 ends up being about 7.54. Now, 7.54 is the number, but what are the units? Well, the 1 pressure, it was ATMs. So this means our answer should be an ATM. Let's see if our inverse relationship held true. So we went from a volume of 196 to 26. So we had the volume go down. Did the pressure go up? Yeah, it went from 1 atmosphere to 7.54. So pressure did go up. So Boyle's law held true. This is an inverse relationship. Sometimes I accidentally call that indirect, but what I really mean is inverse. Let's rock out number 12. This is Gay-Lussac's area. We know the relationship between pressure and temperature. We know that as we increase temperature, it's going to give more energy to the gas, and that's going to increase pressure as long as the volume stays constant. So we've got a gas at a pressure of 699 millimeters of mercury. All right, so that's a pressure, and a temperature of 40 degrees Celsius. We want to know what the new temperature is, so that's going to be our variable. When the pressure is raised to 760 millimeters of mercury. So that's going to be our pressure 2. As we see from up at the top, it's going to be P1 over T1 equals P2 over T2. That's Gay-Lussac's law. Let's start plugging in and getting our answer. Initial pressure is 699 millimeters of mercury, and the starting temperature is 40 degrees Celsius. As we know, we don't want our temperature at 40 degrees Celsius. We want it in Kelvin, so that's really 313. Our pressure 2 is going to be, 760. That's going to go up to. So let's do that. And then last but not least, we don't know our final temperature. That's what we're going to solve for. So we can go ahead and do that by doing our cross multiplying. So 699 times our new temperature equals 313 times 760. Now these numbers might seem big. That's because millimeters of mercury is a larger unit, meaning the numbers are bigger, I should say. So I did 313 times 760. That gave me 237,880. Now we want to get T2 by itself, so we're going to divide by 699 to both sides. And when we do that, T2 is left alone, and we're left 340.31 Kelvin. So the question is, did this direct relationship hold true? The temperature, did it increase if the pressure increased? Well, we know the pressure went from 699 to 760, so pressure increased. Let's look at the temperature. The temperature started at 313 Kelvin and went to 340 Kelvin or so. So as the pressure increased, so did the temperature. Yes, this is a direct relationship, and perfect. We are all set. So this gas law holds true. All right, so this is just a matter of knowing your units, plugging in and chugging out an answer. And remember, for all 3 gas laws, they really are just the combined gas law, PV over T equals PV over T. But when something's held constant, like here in number 12, volume is held constant, we pull that out of the equation, it becomes P over T equals P over T, which is the equation for this gas law. All right, nice job, science fam. Hopefully this helps out a little bit and can get you on the right track. Keep practicing these. You want to be comfortable and confident with them, but also know what's inverse and what's a direct relationship. Take care.